Okay, so here we go again, chapter 7.2, example 3. So we're just going to go through this and then provide a homework after example 4's being done as well. So we begin as usual by reading the questions and seeing what the key information is. So it's a smooth bead. And the key fact here is it's threaded, and we'll talk about what that tells us in a moment. On a light, inextensible string, the ends of the string attached to two fixed points, X and Z, on the same horizontal level. I think that's basically as it's shown in the diagram. The bead is held in equilibrium, a horizontal force of 8 newtons, parallel to ZX. The bead Y is vertically below X. And angle XZY is 30 degrees, as shown in the diagram. Find the tension in the string and the weight of the bead. Okay, so key things. Smooth bead, so there's no friction. The thread is light and inextensible. So those together tell us that the tension is constant throughout its length. Yeah, the force acting on any particle in the string in both directions is the same, because the string is light, it's inextensible, and it is smooth. The bead is smooth, so there's no friction element acting on it. So we can now add on the forces onto the diagram. So we've got a tension acting on the particle along the line of the string towards Z, and a tension acting on the particle towards X. And then we've got the weight of the particle, and we could normally write that as mg, but because the question asks for the weight, here we're just asking for the weight, we can, instead of calling it mg, we might as well just use W. Okay, now, as it's in equilibrium, we know that the sum of the forces in any direction we choose to work is equal to 0. When we look at the system of forces here that we're looking at acting on the particle, we can see that this T, this W are acting vertically. This 8 newtons is acting horizontally. So they are all at right angles to each other. So that suggests to us that the best directions to work are horizontally and vertically, rather than in the direction of the other tension towards Z. So let's begin. Resolve horizontally, and we then need to break down T into its two components. So we've got a component horizontally. This angle here is 30 degrees because these are alternate. Yeah, so these angles here are alternate angles. So we get here t, and it's next to the angle, so it's cos of 30. And then opposite the angle, we've got t, and it's opposite, so it's sine of 30. So now when we resolve horizontally, we can have t not sure why that's not writing. That's it. Okay, sorry. So t cos of 30 minus 8, resolving horizontally, is equal to 0 since equilibrium. So t equals 8 over cos of 30. Cos of 30, we should know, is root 3 over 2. So we've got 8 root 3 over 2, dividing by a fraction, invert and multiply, so 16 over root 3. And then we want to rationalise the denominator, so we can multiply top and bottom by root 3, and we're going to get 16 over 3 root 3. You can tap it in a calculator. That's about 5 and, well, it is 5 1/3 times about 1.7, so it's going to come out to be roughly 9. Bit more than 9, 9.24 to 3 SF newtons. We also need the weight. So resolve vertically, and when we resolve vertically, we're going to have t minus w plus t sine 30. So t minus w plus, I think it was, yeah, t sine 30 equals 0 since equilibrium. So t plus t sine of 30 is equal to w. T we know is 16 root 16. T is 16 over 3 root 3. So take that out as a factor, times 1 plus sine of 30, or sine of 30 is a half. So that's 3 over 2, which makes that